Hey everyone, Mythidas here. Today we're going to be taking a look at the differences since the last devlog, and the main difference is that I've added 3D rendering. So we're going to kind of take a look at what's going on in the editor now with 3D rendering, and just take a look at some of the things I had to solve for adding 3D rendering to the engine. So to take a quick look, I added this little test script to add random cubes to the scene, and let's just go ahead and add like 50. And you can see that the cubes generate fairly quickly, and it's got some pretty good frame rate with 50 cubes. Now, my 3D renderer currently is not a batch renderer. And so if I add like, let's just say like 200 cubes, it's gonna destroy my frame rate. But as you can see, those 200 cubes generate pretty quickly, and that's due to the entity system being solid. It's just the actual rendering code that's pretty slow right now. My 2D renderer is a batch renderer though, so my 2D renderer can handle like 20,000 objects just fine, but when you're doing a draw call for every single one of these cubes, it goes pretty quickly. Now, something that I'm actually doing that's very inefficient right now is that I'm not actually doing a draw call per cube. That is a lie. I am doing 3 draw calls per each cube here, and the reason being, and let me just fix the frame rate. The reason being is if we take a look at a cube, you'll notice that each one of these cubes has 3 colors. But what that means is that each one of these colors is actually a separate mesh. Because the way that a 3D modeling program exports an object with multiple materials applied, because this isn't one material, this is an individual material with different colors applied to it. The way that a 3D modeling program would export that is these 2 faces, the blue faces, are one object, these 2 green faces are one object, and then these 2 orange faces are one object. And so what ends up happening is that this is actually 3 different meshes with 3 different materials. So I'm actually doing 3 different draw calls per object right now, making it very inefficient. And the reason that I'm doing 3 draw calls per object for it having 3 different meshes is because I want to eventually group object calls not by meshes but by materials. So the reason I've left it separate and it's slow right now is because it'll make it a lot easier to move to 1 draw call per material, because all I'll need to do is tie the materials together instead of worrying about all the meshes. Now let's take a look into the differences between 3D rendering and 2D rendering that I found, and how I adapted my 2D code to become a 3D renderer. So to start off with, a 2D renderer is made up of just squares. I have 2 triangles per square with 6 vertices and 4 indices. Now I pre-render all the indices because you know 100% how many indices you can possibly have, and I just pass that into my element buffer object, or my index buffer. And then with the vertices, you of course have to generate those at runtime because you need to know things like position, rotation, color, etc. And the way that you would render something that isn't a square, like a circle or a triangle, is you still render a square, but you just apply a texture. So if you go make a texture of a PNG of a circle and then you leave some of the pixels to be transparent, then there you go. You've made a circle just by applying a texture. And so that's how my 2D renderer works. And in the 3D renderer, you need to actually do your indices at runtime as well, because you don't know what your indices are going to get passed as for each 3D object, because a 3D object can be very complex, or it could just be a square. You don't know what's going to be passed into the engine. So the way I have done that is I've done a vector of unsigned integers, and then that vector gets passed into an OpenGL call, and I'll show how that works in a moment, because it actually confused me a bit of how to get a vector to work inside of an OpenGL call, because it's not just a raw array. So that's going to be something I'll show off. But to start off with, we're going to just take a look at how I solved the multiple meshes and multiple colors issue. Because like I stated earlier, each cube actually ended up being 3 meshes and 3 materials. And instead of doing 3 different meshes, I wanted to keep everything inside of 1 mesh to simplify the space requirements it takes to have a 3D object when it comes to memory. Because if I want to have 3 different arrays, I would need to allocate 3 different vectors, and that actually adds some overhead that I don't want, because currently with the cube only has 3, but what if you had an object with 20 different meshes? I know that's pretty ridiculous, but it's possible. And so instead of doing 20 different arrays, I've done one array, and then each submesh is what they're called, is actually just based on an index. So if you have a submesh at index 12, then you would get all the vertices and indices from 0 to 12 within the array. And I believe that's actually how Unity handles it well, because that's where I got the idea from. And so we're going to take a look at a piece of code right here. And this is right in the render. If I pass in a mesh, this is kind of what goes on to tell what's going to happen to that mesh when I render it. So we start out by looking at the submesh count. And the submesh count just returns a size, or if it is 0, then we want to go ahead and just render a single mesh using the provided mesh. Now, the way the materials works is it's always going to pull the first material of the array if you're only rendering the main mesh. The reason being is that I can't tell where another material would need to go. And so I just apply one material to the whole thing. And then after I've applied that first material in the array, I just go ahead and draw my mesh using this draw mesh call. Now, if I have any submeshes, it's going to loop over those. And I'm just going to get a new mesh using get submesh, which is just a function on a mesh that would return a new std vector from that 0 to 12 position. And then if your offset was, the next offset was 24, it would take the previous offset, so it would go from 12 to 24. And so on and so forth, depending on where your submesh index was. Now, I also need to grab a material from the index that we're currently at. If there isn't a material at the index, I do have this call called asset manager get default material, and this just returns a material that uses a white texture, just so that if nothing's there, I can at least render white and it doesn't just become transparent. Because if I don't have a material in this box, it will just show up as transparent and show nothing. And then instead of passing in the mesh vertices, UVs, and all these arrays, I now just pass in the submesh. So it's pretty simple of how that implementation worked, but it was very confusing to get all those meshes back from async, because before I would end up having 3 meshes, and I didn't want to have a mesh array on my mesh renderer object because it just didn't make sense when it came to serialization. Because now instead of serializing 3 different meshes all to the same objects with a bunch of indices or indexes, I just simply serialize out one object in one mesh, and it's much simpler when it comes to that, saving and loading an object. When it comes to drawing the mesh, it's all pretty simple. You're just inputting vertex information and index and a number for an index buffer into an array. So we're not going to show that off. If you want a more deep dive over 3D renders, then let me know. But down here is where we end the batch, and I wanted to show off how I'm using the index arrays, just in case anyone else wanted to use an array versus a pointer or a actual array. So for the index buffer, I'm using the size of index buffer 0 to get the first element, because this is basically going to return a unsigned int. So it's going to take the size of unsigned int and multiply it by the size of the actual index buffer. And so once I get the size of this multiplied by how many I need, then I just pass in sdata with the index buffer.data. Now, I have tried passing in the front object and it hasn't worked, because an array, when you have an array, every item in the array is sequential. So if I pass in sdata dash index buffer, and then if I were to do dot front, it would pass in the front item, and you can actually do that, and it should be able to loop from the front item to the last item, but I couldn't get that to work. And the reason it's throwing an error is you need to pass it as a reference. And this is what I was finding online, but I couldn't get that to work. So instead of passing that, I literally just passed the data block, because this just passes in the actual raw pointer to your data rather than a reference to the beginning of the array. Now, after all that, it's pretty simple. When it comes to the index buffer here at the bottom, I'm using GL draw arrays, and I'm just getting the size of my index buffer to tell me how many indices I have. Now, GL draw arrays is actually interesting here, because I used to use GL draw elements, because I thought that you needed GL draw elements for if you're using a GL element array buffer, and I actually could not get GL draw elements to work inside of my 3D renderer. It would create like random fragments of like vertices being in the middle of space and creating these huge lines everywhere if I had things spaced out, and it just wasn't working. So instead I changed that GL draw elements to GL draw arrays, and all my problems went away when it came to renderer calls. Now this is pretty much the biggest difference when it comes to 2D versus 3D rendering. And the only other thing that I've implemented since the previous video is actually this class called model importer. And this model importer class basically just loops through a model provided by the async library and just renders that all out. And so I do have some helper functions in this class, like generate entity, because I can create a new model importer item and it'll load the model. And then after I've loaded the model, I can just call generate entity on it. And instead of having to loop through it in a separate class and figure all that out, the model importer can use all the internal information that I pulled from the meshes and just create an entity from that. Now, a quick look into the processing of the mesh inside of my load model function is just to take a quick look of how I handled adding submeshes. And so the way I did that is at the start of a mesh, because I'm going over the number of meshes within this node, is I would do an indices start, which is just the size of the indices. So for a 0, it's going to return a size of 0. And then after I process all of the information, I come down to the bottom and I use my mesh and I set a submesh, and it takes a start and it takes an end size. And so the ending is actually just going to be the size of an indices minus 1, because when you access the array, you're going to need to make sure that it's minus 1 so that you're accessing it by index count and not by the actual size, because size will return 1 if you have 1, but the way you access the first is actually with a 0. And so that's how I've implemented set submesh, is it's literally just an index start and an index end, and then it can pull that from the meshes. So for this week, that's pretty much all of the changes. There were some other minor changes, but for the most part, it was just 3D rendering that I was trying to implement, and I had to do a lot of changes to the internal asset management code to actually get that working. And currently I'm actually going through a rework of the asset management, because the biggest bottleneck right now when it comes to importing model, because this is a single imported model, so I'm just duplicating the information. But if I were going to import a bunch of different models, the biggest bottleneck I have right now is the fact that I have to generate a material. And if I try to import the same model, because if I was going to like import, like, let's just say a cardboard box into my scene, and I was going to duplicate that cardboard box everywhere. Right now, I'm making a new material every time I import that asset. Whereas I'm trying to rework the asset manager so that when I import a new material from async, I can find that material later if I have that same asset loaded somewhere else. So materials and meshes are the biggest bottleneck right now when it comes to how fast this rendering code works. And that's why when I add so many more draws, it's just totally bottlenecking everything down, because now I'm not rendering one material, right? This orange stuff isn't all one material. This is actually, for every single one of these cubes, I have 188 times 3 materials rendering. I have 188 times 3 submeshes rendering at the same time. So I need to fix the asset management so that that's not 188 times 3 materials. It's actually just 188 draw calls, because then I don't have to loop through every single material again. But that's why this is running slow. So if you guys are implementing your own 3D renderer, that's kind of something to look out for. Is I would suggest batching by material, just because of the way that 3D rendering, there's not really a great way to just batch by a single object. But I hope you guys enjoyed, and I hope you guys enjoy seeing the progress of the engine. Like I said, if you guys want to deep dive over anything I've done, please let me know and I will make a separate video on it. This next week, I'm going to try to make a video over how I implemented serialization inside of this engine. And I'm going to try to show off 2 methods, actually, because I created one method and it was fine, but I wanted to create a different method just to see if I could implement it in a different way. And I actually prefer the second way because it doesn't use any macros. So if you guys enjoyed, please leave a like and please leave a comment if you want to see anything else. and I hope you guys enjoyed this video, but I'll see you guys in the next devlog.